Next, we'll discuss the flagship application for this thesis and the original work that piqued our interest in compressive parametric estimation, which is compressive match field processing. So here we have an acoustic source located somewhere underwater that we want to localize. So we listen with some array of in receivers and we try to figure out where it is. So here, if you imagine that some transmitted wave is happening with some complex amplitude alpha and frequency omega, then this received amplitude is going to be some other complex amplitude, we'll call it yn, at each of the n receivers, times e to the j omega t. This is for any linear time invariant system. So now the goal is, starting from these received complex amplitudes, to try to estimate this the transmitter's source and depth. So here, these Green's functions are describing this linear time invariant frequency response from r naught to each of the n receivers. So this is just something that maps some source location to a vector that's complex in Cn. And so we observe this observation y, and to solve this we do classical least squares assuming Gaussian noise, which is just we minimize over both r and beta this residual error of y minus beta gr, or equivalently we can maximize this ambiguity function. So this fits very nicely into our framework in terms of the compressive subspace matching, because we're simply applying a projection matrix to this data vector y. This normalized inner product basically is just dividing by the norm of each vector before taking this inner product. So this is what an ambiguity function looks like as a function of range and depth. So here we're just maximizing this function. So as you can see, there's a clear winner for where the maximum is. And what we want to do is put a twist on this. So instead of maximizing this ambiguity function, we want to maximize this compressed ambiguity function. We want to work with phi y and phi times g of r and come up with this guy instead. So this is what the compressive ambiguity function looks like, and it's very similar to the classical ambiguity function. It just has a bit more noisy, it doesn't look quite as clean, but the important thing is that they share their maximum in a common place. So why do we want to do this? Well, the adjoint operation is difficult to compute over a given range. So it requires n PDE solutions to come up with this Green's function g of r, one for each receiver in general. So instead, we can do something called time reversal, which is computing one PDE solution for each y, but it gives suboptimal performance because it's unnormalized. So we offer a nice middle ground, basically. We instead compute m PDE solutions instead of n, and we can compute this offline independently of y, and it can be reused for all future instances. But it provides a speed up of n over m, and so we'll give specific examples of what this speed up will be in a second. So far we've been talking about single frequency for the case of simplicity. Now let's talk about how this applies in the broadband regime. So suppose that you have a source that's transmitting with known frequencies and known amplitudes, but you have some unknown global attenuation beta. Then you can set this up as a least squares problem, where again you're minimizing over r and beta, but now you've stacked up all of the received vectors for each frequency between y1 and yk for each of the k frequencies. And this ends up being a minimization over the sum of squares of these residual vectors. So because this resembles exactly the single frequency formulation, we can solve it with exactly the same sort of approach, just by stacking these elements together and applying the standard solution. Now on the other hand, suppose that we have the same setup, but now each individual source amplitude is unknown for each frequency. So this is the general case where we shouldn't expect to know what spectrum the source is transmitting with. So in general, we need to estimate all of these, and instead we're estimating each beta k by itself. And this is equivalent to summing together the normalized ambiguity functions. You can show this. Okay. So now let's show results, and before we show some results for this approach, we're going to instead define the distance metric that we use. So for these approaches, the distance in depth is much more sensitive than distances in range. So in range, we will have rather large errors, and in depth, we'll have very small errors. So in order to sort of equalize these two elements, we're going to use an elliptical metric instead. So here in the inner circle, we're showing the ellipse corresponding to a unit distance, and then the one further out is a distance of 5, and the one further out is a distance of 10, just to give you an idea. So with that distance metric in mind, this is the sort of the results for the single frequency case. The dashed blue line is standard match field processing. So, and the dashed green line is the normalized match field processing. This is if you do proper normalization using the denominator. So the blue line is faster than our approach. It only takes 1 PDE solution. The dashed green line takes 37 PDE solutions. And the solid lines take somewhere in between. So for using 3 measurements, we end up doing much worse. But starting around 6 measurements, we start to do better, at least than the unnormalized match field processing. And by the time we get to 20, we're mimicking very closely to the full approach that takes 37 PDEs. So we offer a nice middle ground. And so, for example, this offers a speed up of 37/6 compared to the full match field processing. So likewise, in the coherent regime, with only 2 measurements per frequency, we're able to mimic very closely to the normalized match field processing. So this is the cyan line here. And so this offers, again, a speed up of 37/2, so about a factor of 18 times faster. You can end up with an approach which works almost as well as the normalized match field processing. And in the incoherent regime, again, you have, for the dashed lines represent the classical match field processing, either normalized or unnormalized. And our approach, using only 2 measurements per frequency, does fairly well at a speed up of about 37/2 times faster. This is showing how this approach works with variable noise. So the way that you read this plot is that we can come within a certain distance with a certain probability under this noise regime using 20 measurements. And this plot shows the same information, except that instead of having variable distance, we're fixing the distance at a distance of 1. So anything that's inside this ellipse is considered success. So we're showing the failure probability, the probability that you localize somewhere outside of this ellipse using a variable number of measurements over a variable noise level, signal-noise ratio, basically. So the way to read this is, for example, if you want 90% recovery probability using only 10 with a 8 dB signal-noise ratio, then you'll need at least 10 measurements. That's one way of looking at this plot. And this shows the relative accuracy between compressive match field processing and classical match field processing along some moving target. So here we're not using any prior knowledge from the previous estimate. We're just estimating each location independently. So obviously it could be improved by something like a Kalman filter approach, but this is just a standard way of illustrating.